Welcome to this comprehensive guide on data structures interview questions. Data structures are fundamental building blocks in computer science that help organize and store data efficiently. Today, you'll learn about essential concepts including arrays, linked lists, stacks, queues, trees, and graphs. Understanding these structures is crucial for technical interviews and building efficient software solutions. Each data structure has unique characteristics that make them suitable for different real-world applications. By mastering these concepts, you'll be well prepared for coding interviews at top tech companies. Arrays are one of the most fundamental data structures in programming. An array stores elements of the same data type in contiguous memory locations. Each element can be accessed using an index, starting from 0. Arrays have a fixed size once created, and elements are stored sequentially in memory. The key advantage of arrays is constant time access, meaning you can retrieve any element in one-time complexity. Arrays are cache-friendly due to their contiguous memory layout, which makes them ideal for scenarios requiring frequent random access to elements. Understanding time complexity is essential when working with arrays. Accessing an element by index takes one time, making it extremely fast. Searching for a specific value requires checking each element, resulting in n time complexity in the worst case. Inserting an element at the end of a dynamic array typically takes one time, but inserting in the middle requires shifting elements, leading to n complexity. Similarly, deleting an element from the middle requires shifting remaining elements, also taking n time. These complexities help determine when arrays are the best choice for your application. Linked lists offer dynamic memory allocation, solving the fixed size limitation of arrays. Each node in a linked list contains data and a pointer to the next node. Unlike arrays, linked list elements are not stored in contiguous memory locations. The main advantages include dynamic size adjustment, efficient insertion and deletion operations, and memory efficiency when the size varies frequently. However, linked lists lack random access capability, require extra memory for storing pointers, and have poor cache performance due to non-contiguous memory layout. Understanding these trade-offs helps choose between arrays and linked lists. Stacks follow the last-in first-out principle, similar to a stack of plates where you can only add or remove from the top. The 4 fundamental operations are push to add an element, pop to remove the top element, peek to view the top element without removing it, and is empty to check if the stack is empty. All these operations execute in one-time complexity, making stacks highly efficient. Stacks are essential for function call management, expression evaluation, undo operations in applications, and solving problems like balanced parentheses checking. Queues implement the first-in first-out principle, resembling a line of people where the first person to join is the first to be served. The main operations include enqueue to add an element at the rear, dequeue to remove an element from the front to view the first element, and is empty to check if the queue is empty. All operations run in one-time complexity. Queues are fundamental in breadth-first search algorithms, task scheduling in operating systems, handling requests in web servers, and managing resources in multi-threading environments. Binary trees are hierarchical data structures where each node has at most 2 children, typically called left and right child. The topmost node is the root, nodes without children are leaves, and the longest path from root to leaf determines the tree height. The depth of a node represents its distance from the root. Binary trees excel at representing hierarchical relationships like file systems, organizational charts, and decision-making processes. The binary property ensures efficient searching, insertion, and deletion operations when the tree is properly balanced. Tree traversal refers to visiting each node in a systematic order. The 3 main depth-first traversal methods are Inorder, preorder, and postorder. Inorder traversal visits left subtree, then root, then right subtree, producing sorted output for binary search trees. Preorder traversal visits root first, then left subtree, then right subtree, useful for creating copies of trees. Postorder traversal visits left subtree, right subtree, then root, commonly used for deleting trees or calculating space requirements. Each traversal method serves specific purposes in different algorithms and applications. Graphs consist of vertices, also called nodes, connected by edges. Graphs can be directed, where edges have direction, or undirected, where connections are bidirectional. Weighted graphs assign values or costs to edges, while unweighted graphs treat all connections equally. A connected graph has paths between all vertex pairs. Graphs model complex relationships in social networks, transportation systems, computer networks, and dependency relationships. Understanding graph properties helps choose appropriate algorithms for shortest pathfinding, network analysis, and connectivity problems. Data structures power countless real-world applications. Arrays handle database storage and image processing, where pixel data needs efficient access. Stacks manage browser history for back and forward navigation and handle function calls in programming languages. Queues control task scheduling in operating systems and manage print jobs in spooling systems. Trees organize file systems with directories and subdirectories and power decision-making algorithms in machine learning. These practical applications demonstrate why mastering data structures is essential for building efficient software solutions and succeeding in technical interviews.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.